today's lesson objectives are going to be: one, we're going to be familiar with the definition of an indefinite integral as a result of reversing the process of differentiation, which we have covered before. We're going to understand how the rules for integration are worked out using the rules for differentiation in reverse. We're going to be able to find indefinite integrals of sums, differences, and constant multiples of certain elementary functions. And lastly, we're going to be able to use the chain rule in reverse to find indefinite integrals of certain expressions involving composite functions. So before we continue, I want you guys to test yourselves on your differentiation skills. And I'm going to give you guys two examples in which you guys can pause the video and take some time to practice doing differentiation, and you can use this as a gauge for you to see if you're ready to cover integrals. So take a minute or two to test yourself on these two derivatives. So find the derivative of each of these two functions right here. And now that you have taken a second to do those problems, check with this. These are the solutions to both of those problems, and check that you have been able to complete this problem to get this solution. So these are two solutions you should have gotten. Okay. Now, knowing that you are ready to, you are comfortable with derivatives, we can start looking at integrals. And the basic definition that we're looking at right now is, let's say that if we have a function, so let's say that we have a function, we have the derivative of a function. So derivative with respect to x of the function f of x. And let's define that as the derivative being f of x. So little f of x. So the derivative of big F of x is equal to the derivative of little, or is equal to the, it's equal to f little fx. Then the definition of integrals states that if we take the integral, this is the symbol for integral of the function, the little f of x with respect to x, that is going to give you f big F of x. In other words, the derivative of big F of x is small f of x. Then we can say that an indefinite integral of f of x with respect to x is big F of x. One example that can easily show this relationship is, let's take a look at what the derivative of x squared is. And we know by what we've learned that the derivative of x squared is going to be equal to 2x. Right? So if we write this, we know that the derivative of with respect to x of the function x squared is equal to 2x. Knowing this, and using the definition we have just talked about, we can say that the integral of 2x with respect to x is equal to x squared. So there's a very close relationship between taking the derivative and then doing the integral. One thing that I do want you guys to know right here is that this right here is an indefinite integral. And notice that I didn't say the indefinite integral. And that's because we know that when we take the integral, for example, of, with respect to x, of, let's say, x squared plus 3, we know that that's going to be equal to 2x. Right? But you should notice that this is not equal to this. This other one that we found right here. And the reason for this is that there exists a constant c that if you take the derivative of let's say for the function, so now let's go down here, let's say for the function d of dx squared plus c, we also get 2x, meaning that if we take the integral of 2x dx, that should be actually equal to x squared plus c. C is any constant, and this c can be found using the limits that you are given. And for our sakes, we're not going to be learning how to determine the value of c, but just know that what we have found right here, x squared plus 3, x squared plus 4, and so forth, that those are examples of the indefinite integrals of 2x. But for our sakes, the term c is going to drop off whenever we take the integral of any function. Now let's take a look at some rules for integrating different functions. So these are going to be our rules for calculating integrals. And we're doing different colors. We have rule number 1. Something that you should know is that the rules for integrals are derived from the rules for operating with derivatives. So for one example that we have looked at before when we were looking at derivatives is when we have the derivative with respect to x of a function f of x multiplied by a constant c, we remember that the c goes to the front because it's a constant, and we just take the derivative of the function with respect to x. So that was a derivative rule that we saw in our last video, and this works for any constant, c, constant being a real number. And from this we can derive the rule 1, which is if we take the integral of c times f of x dx, what we can simplify this to is we can take the c out of the integral and do the integral of f of x with respect to x. And this works for any constant c. One example that I can do for you guys right here so you guys can see this process is, let's say that we want to take the integral of 10 cosine x dx. Okay, so using this rule, this right here is the constant. This value right here, the 10, is this constant c. This constant c. So because we see in this rule that we can take out the 10, we just are now worried about the integral of cosine x dx. One thing that you guys will learn and will have to memorize is that we know that the derivative of d of x, derivative with respect to x of sine x, is cosine x. So if we work backwards, then the integral of cosine x is going to be sine x. So then this would yield a solution of 10 sine x plus the value of c, which in our case will drop out as 0. So it's going to end up being 10 sine of x. This is the rule. This is rule number 1. Whenever you have a constant in front of your function, you can take it out of the integral and integrate it as if you were just working with the function and multiply it times the constant that you started with in the beginning. Another way that you guys can think about this is you can move the constant past the integral sign without changing the value of the expression. And this is similar to when we were looking at the derivative of f of x plus g of x. We can just take the derivative of those functions separately and it will not change the value of the expression. All right, rule number 2 now. And this rule is defined by the following. If we take the integral of f of x plus g of x so if we're taking the integral of f of x plus g of x with respect to x, we can say that that's the same as taking the integral of d of x, of f of x d of x plus g of x d of x. So doing this does not change the value of our expression, so we can do this. This is a rule. One example that I can give you guys so you guys can see this is now this rule is similar to the one that we saw back when we were doing derivatives, and that's why we know that the taking the derivative should be familiar to you as being related to what we were doing with doing integral should be related to what we were doing with derivatives. And this is the example that we're going to look at. For example, if we're looking at the integral of cosine x plus 2x with respect to x, we can simplify this to the integral of cosine x plus d of x plus the integral of 2x d of x. Now taking these separately, we again, same rule that we use here, we know that the derivative of sine x is cosine x, so the integral of cosine x should be sine x. So right here we have sine of x plus the integral of 2x dx, which will give you x to the power of 2. So what we do here is we add 1, so it was 1, we add 1, and we divide by the sum. So we add 1 to the exponent, and then we divide by whatever we get here. So that should be equal to sine of x. X becomes plus x squared. 2 divided by 2 is 1, so then we can cancel those out. And just note that right here, we divide by this value, the value that is increased in the exponent. That's what we get here. Okay. In other words, one way that we can put this in words is that the integral of the sum of two functions is the sum of their integrals. We can easily include this to extend to differences also if this was a minus. In the case where we have more than two terms, if we have three terms, if we have cosine x plus 2x plus sine x plus tan x, then we can do we can take the integrals of each one of those separate functions and get the answer for that. As a check for understanding, I want you guys to practice doing one on your own. So I'm going to give you guys an example of an integral I want you to take, and I want you to pause the video and try it on your own. And the integral that we're going to be looking at is the integral of 3 cosine x minus 1/2 x squared. And all of this is with respect to x. So pause the video and try this one on your own. Now, hopefully you took some time to solve this, and at the end you should have gotten that the integral of those functions is equal to this right here. Now let's look at rule number 3. And rule number 3 is as follows. If we take the integral of x to the power of n with respect to x, then the solution for that is going to be 1 over n plus 1 times x n plus 1. So you saw this when we used it for the previous problems. But now we're going to take a closer look at what we have right here. And this is the basic rule for integral for a polynomial or for any expression. So what you do is, again, let's highlight it, the exponent, to take the integral, you take the exponent and add by 1, and that value you divide to the entire function. And this might make more sense with some examples, so we're going to look at a couple examples, and one example that is an exception to this rule. The first example that we're going to look at is when we take the integral of x to the third d of x. Again, using this definition, we can see that right here, well, we know that n is equal to 3. Just from here, we know that n is equal to 3. This right here is the value of n. So now knowing that this is equal to 3, we can replace it into this definition. So it's 1 over 3 plus 1 x 3 plus 1, and that all of that is going to be equal to x to the fourth divided by 4. So again, the simple way to do this is just to think about this exponent, add 1 to that exponent, and divide whatever value you get for the new exponent to the function. Let's take a look at another example. The integral of 1 over x squared d of x. Now for this one, it's easier if we rewrite it using our exponent rules. So that should be x to the negative 2 d of x. So if we do this, now we know that n is equal to negative 2. And by that we can see that it's 1 over negative 2 plus 1 x negative 2 plus 1, which is going to give us a value of x to the negative 1 over negative 1. Simplifying this, we can see that that's negative 1 over x. So that's the basic definition for taking the integrals of any function. One exception that I do have to point out, so this is an exception to the rule, and you have to be able to recognize this exception when you are doing it on the test, and that's when we have n equal to negative 1. So for example, if we have x to the negative 1, by the definition that we have seen, we know that x is equal to negative 1, meaning that the solution is going to be 1 negative 1 plus 1 x negative 1 plus 1. Something that you should notice here is that we have x to the 0 over 0, and we know that we cannot have a 0 in the denominator. So for this one, what we have is a very special rule that we have to be able to recognize, and then know that with derivative of with respect to x of the function ln of x is going to be equal to 1 over x. Therefore, the integral of 1 over x, or in other words, if we write this as the integral of x to the negative 1, is going to be equal to ln of x plus c. But we know that again that the c drops out, so it's just ln of x. Now, at this stage, it is very tempting to give you a list of standard integrals corresponding to derivatives, and you memorizing those derivatives and integrals and being able to recognize it. However, you are not encouraged to just memorize the integration formula, but rather become familiar with the list of derivatives and practice recognizing a function as the derivative of another function. If you try to memorize both differentiation and integration formula, you are going to one day mix them up and use the wrong one, and therefore there's no need to memorize the integration formula if you know the differentiation ones. Now, it is much better to recall the way in which an integral is defined as an antiderivative, and that's something that I'm going to define right now. And this is an easy way to remember this. So the antiderivative that I just talked about they're just basically the opposite of derivatives. All that means is that an antiderivative is a function that reverses what the derivative did. In other words, it's also what we know as the integral. So this is very important because what we're doing when we're taking the integral, or we're doing it, is working backwards to what we did with the derivatives. This is very important because every time you perform an integration of any function, you should take a second and check it by differentiating your answer to see if you get back the basic function that you began with. This is a very important habit to develop as you guys do the integrals of different functions, and this will avoid making a lot of mistakes. There are many different tables that exist that will show you the answers of different derivatives, but try to avoid using it if you can, but do refer to those tables if you are unsure. Let's do one example to crystallize this idea in your mind. And the example that we're going to do is taking the integral of e to the power of x plus 3x to the 5/12, all of this with respect to x. Now for this one, what we're going to do is, again, we're going to use the first rule that we talked about, which is we can do the integral separately. We're also now going to take into account that we know that we can take constants out of the integrals. Now, one rule that you will learn later on, as you're memorizing the different special rules for derivatives and integrals, is that if you take the derivative of with respect to x of e to the power of x, that's just e to the power of x. So whether taking the derivative or the integral, it's going to be the same. So the integral of e to the x is just e to the x. Now let's do the integral for this one. So it should be 3, and we're going to use the rule. So it should be times 1 over our n in this case is 5 over 2. We're going to add 1 to that, and then we have x 5 over 2 plus 1. Continue. And so we have 3 times whatever this is. So in this case, what we have here is, if we make this 1 2 over 2, then we have 7 halves. We have x to the 7 halves. Now that simplifies to e to the power of x plus, what this becomes is going to be 2 over 7. So 2 times 3 is going to be 6 over 7 x to the 7 halves. And we had a constant c, but for our sakes, we're just going to set that equal to 0. So again, this is also, so integrals are an example of antiderivatives. And now let's take a look at what we have here and use this definition of antiderivatives to see if we can get our original function by finding the derivative of our answer. So this is how we check. It is very important to get in the habit of checking your integrals by taking the derivative of that to make sure that you are not making a mistake. So we have in this one, and I'm going to do it in a different color so you can see the difference. This is going to be in purple. Okay. So again, we know that this is a sum, so we can do them all separately. Okay. Now again, because of this rule, we know that the derivative of e to the x is just e to the x plus, now let's do this one. Using our derivative rules, then we know that it should be 7 over 2 times 6 over 7 x 7 over 2 minus 1. In this case, I'm not going to put minus 1, but I'm going to put 2 over 2, which is equal to 1, plus the derivative of a constant is 0. We have e to the x plus 7 times 6 is 42 over 14 x 5 over 2 plus 0. If we continue, we can get that that's equal to e to the power of x. 42 divided by 14 is 3. X to the 5 halves. And that's a 0. So this is our answer. So if we take a look at this, when we took the derivative of our answer, we got back our original function. This is the best way to make sure that you're not making a mistake, and try to get in the habit of, when you take the integral, also take the derivative of the answer to see if you get back the original expression which you were integrating.